Hi and welcome to video 2 of this Unit 3 Specialist Mathematics matrix work. So this is part of the vectors and matrices topic, and we're just reviewing matrices because we're going to go towards solving systems of linear equations. You may or may not have covered the Gaussian elimination by now, and that's the other variation on how we can solve systems of linear equations. This is how we do it using matrices. So first in exercise 7c, which is the dot point here, is just solving 2 by 2 matrices using, 2 by 2 systems of linear equations using matrices. Well, you have done this in Unit 2, so just keep that in mind. It should be a revision. So here's a 2 by 2 linear matrix. Now it's important to note here, obviously, that I'm pretty sure you will be capable of doing this algebraically. And in fact, this is not even going to save necessarily that much time. But it's a process that's important as we get to 3 by 3, 4 by 4, n by n. It's really important to understand, and we learn it through this 2 by 2 system. So what we say is that this can be transformed to be 2, negative 4, 4, 1, and this is the coefficient matrix, times by x, y, and this is called the variable column matrix. Notice here if I expanded that out, I would get the actual left-hand side of the equations, and this is equal to 927, which is the solution matrix. So we can do that change there, and we'll get back to that in a minute. Once we've defined a, x, and s, well, we get this equation here, which is a linear equation for matrices. Ax equals s, and you can see what I've got up here. Ax equals s. Now you might recall that with matrix algebra, we have to be very careful because it's not commutative. Now commutative is not a word that you might necessarily know off the top of your head. It basically means that we can't just swap it around. Ax doesn't equal xa necessarily. In some certain situations it does, but not necessarily. Not like in our number system where we are very confident that 3 times 7 is actually also equal to 7 times 3. In matrix algebra, we just don't know. So we can't assume that it's true because it's not always true. So instead of doing some sort of like divide by a matrix to solve for x, well, we don't know how to divide matrices and we don't want to swap it around. So because a is on the left-hand side, we multiply by a inverse on the left-hand side, and we have to do it to both sides, so we multiply the other side by a inverse also on the left-hand side. Now, we do this because a inverse times a, by definition of what an inverse is, takes us to the identity matrix I. So we now have Ix equals A inverse S, but I is the identity matrix because it doesn't make a difference, doesn't change a matrix. So we don't need I there, we now just have X equals A inverse S. But it's important that A inverse is on the left-hand side of the S. So our rearrangement for the equation above, AXS, is that we get XY equals A inverse 927, and A inverse is the determinant of D negative B, or 1 over the determinant, sorry, times D negative B negative CA, and the determinant is 18 in this case, so we get 1 over the determinant, 1 over 18 times 1, 4, negative 4, 2, and we multiply all that out, which we can do, and it comes out with something not brilliant, but that's not too bad, 6.5, 1. And this is all just a little bit of maths here. But a lot of questions that you do in Unit 3, you'll be doing 3 by 3 or 4 by 4 matrices and relying on a calculator. So x is equal to 6.5, y is equal to 1. We can evaluate this by substituting them back in. So I go back up to the original equations here. 6.5 and 1. 2 times 6.5 is 13, minus 4 times 1 is 9, that works. 4 times 6.5 is 26, plus 1 is 27, so we're pretty happy with that. Recall also that matrix equations, and I'm talking about all matrix equations, not just 2 by 2s, well, if the determinant equals 0, we can't do 1 divided by the determinant. You can't do 1 divided by 0, so this has no solutions, or maybe it has an infinite number of solutions. Maybe a couple of the equations are equal, and that just created an infinite number of solutions. If the determinant doesn't equal 0, then we definitely have one solution. In most cases, we have one solution. And if we go down and show this in orange, we have no solution there is parallel, but if it's the same line, then there's infinite solutions. When we get into 3 by 3 and 4 by 4, we're talking about planes and even beyond. So the lines is a bit easier to visualise. And then I've got an example here to cover off on 7c. Determine the values of m such that this sol being my shorthand way of writing systems of linear equations, has a single solution. Well, remember, a single solution means that the determinant of a must not equal 0. And this is determine the values. It might be written in the exam as /s or something like that. Anyway, so I've got A is the coefficient matrix, which in this case is 2, 3, 1, negative m. And that means that the determinant of A is equal to 2 times negative m minus 3 times 1, which is negative 2m minus 3. And we want this to not equal 0. So we want negative 2. Let's explore, when does negative 2m minus 3 equal 0? When negative 2m equals 3, and when m is equal to negative 3 over 2. So therefore, one solution when m doesn't equal negative 1.5. Any other value of m, and we will have a solution. Because that m here actually defines a gradient. So if m is negative 3 over 2, then we have these parallel lines. Or maybe the same line over again. Whereas if m is not 3 over 2, it means we have the first line, the top one looks like this still, but the bottom one has a slightly different gradient. Maybe like this, or maybe like that, or maybe like this, or maybe like that. But now there's definitely a solution. Okay, so that covers off exercise 7c, and I'm suggesting here, it's not a big one, that you cover all of them. But again, you know, you are in year 12, and you make your own decisions. All the best.